Okay, here's some lesson notes on section 1.3.1 in your textbook. It's on law of sines and area. So we're going to start with taking a look at a brand new area formula for a triangle. The usual formula works great for most triangles, but if we are missing the height, it's kind of tough to find the area of a triangle. So this is a different type of formula that will help us out with that. So part A, it says to write an expression for the area K, and call it K, of triangle ABC at the right. Okay, so for part A, the area K would be base times height, A in this case, times H divided by 2. Or it could say K is 1/2 times A times H. Okay, so for part B, it says using angle C, here's angle C, and hypotenuse B, so this angle and this hypotenuse, find an expression for the height H. So this side right here. So I would say that if we do the sine of angle C, because here's our right angle, here B is our hypotenuse, and from angle C, H would be our opposite side. So sine of angle C is equal to opposite over hypotenuse, which really I wanted to write H over B. And let's solve this for H so I know what the H is. So multiply both sides by B, and we end up with B times the sine of C is equal to H. Okay, part C. Now combine the results from these two parts. So we're going to do some substitution. I'm going to rewrite this part, but in place of my height, I'm going to put this by substitution. So now I've got the area K is equal to 1/2 A times B times sine of C. And this is our new formula right here for area. All right, let's give that a try on an actual problem. So turn to the next one, number 91. So here again is our formula for finding the area of this triangle. I'm going to go ahead and keep that capital K. So here's my angle C, and sides across from angles are always matching. A lowercase c would be over here if this is uppercase angle C. And then these two, it doesn't really matter which is A and B. I could go ahead and call this lowercase a, then that would make this capital A. If I made this lowercase b, then this angle across from it would be uppercase B. So let's go ahead and plug in our information into this. So my area is going to be 1/2 the side A is 4 times side length B 6 times the sine of C. So we'll do sine of 6 or 76 degrees. Now we just put this in the calculator and find the result. And it should be 11.64 square centimeters. All right. Next, law of sines. I think we did a little bit on this in Algebra 2 or in geometry Yeah. Anyway, we're going to take a look at where law of sines comes from. So in the figure at the right, we have our small side links, A, B, and C, and opposite is the capital letter that denotes the angle. So it doesn't matter which one's A, B, and C, just as long as we're recognizing that a capital C and its opposite side, a lowercase c, that they kind of match and the same all the way around. So use the diagram to follow these problems. So A, write an equation to express H in terms of angle A and side B. So kind of like what we did before. So here's angle A, and we want H and B. Well, it's the same thing we had on the previous problem. It's opposite over hypotenuse. So we have sine of angle A is equal to the opposite H over hypotenuse, which is labeled B. There we go. Next, write an expression to express H in terms of B. You know what? I'm not actually done. It says express H in terms of these two. So I need to get H by itself. So if I multiply both sides by B, I'm all set. So the height H is B times sine of A. There we go. All right, so for B, same kind of idea. We want height in terms of angle B and side A. Well, from angle B, it's opposite over hypotenuse, so again, it's sine. So sine of angle B is equal to opposite, which is H, and hypotenuse, which is A. H over A. And then let's solve for B. Let's multiply both sides, solve for H, multiply both sides by A. So we get H is equal to A times sine of B. Okay. Use your results to show that this is the case. All right. Since the height is the same for both triangles, I'm going to put these two pieces together with substitution. So I've got a statement that says B times sine of A equals small a times sine of capital B. All right, now can we transform this so that it looks like our example over here? Sure we can. Divide both sides by B and both sides by A. The A's crossed out and the B's crossed out, and what we have left is sine of A over A and sine of B over B. Okay. D, when we drew an altitude AB, we got this ratio here. If we drew a different altitude, perhaps from B to C, an altitude or a height going this direction, then we would be doing the exact same pattern with slightly different letters. So if we put all of those results together, basically that says that sine of A over A is equal to sine of B over B. And if we'd used two different sides instead, we might have also a sine of C over C. Okay, now this is a little bit confusing right here. We actually only use two pieces of this at a time to do a problem. But we write down all three of them, remembering that it can be any combination of any side and angle, any two of them. So you could do A with B or A with C or B with C and be able to solve a triangle using the law of sines. So here we are. This is the law of sines. Okay, next. Okay, so 95. A triangle is labeled with angles P, Q, and R. Draw a figure that would represent the correct placement of the sides. So if this is angle P, and this is angle Q, and this is angle R, this is just to clarify the placement of the letters, then we must put small p across, and small q across, and small r across, and those are the labels of the sides. All right. So there's our final math notes. I encourage you, there's a lot more math notes and another example on using the law of sines. I really think you should take a look um, at your book and read all of those, work through it, try to memorize it. All right, our very last piece here, some math notes on degrees, minutes, and seconds. Okay, so think about a clock. Hours is a large chunk of time, but then if we break it down to into its next smallest pieces, it's minutes, and if we break time down into its next smallest piece, it's seconds. And instead of it being in groups of 10, they're in groups of 60s. Well, degrees is based on that same exact idea. So we have degrees, the next smallest unit is minutes, and then the smaller unit of that is seconds. So when working with surveying problems and angles that are expressed in degrees, minutes, and seconds, there are 60 minutes in 1 degree and 60 seconds in 1 minute, just like time. And this is how it's written. So you are familiar with the degree symbol, that tiny little O, so 18 degrees. And then the 10 with one little mark here, that would stand for minutes, and then 30 seconds, a double mark. So it's translated to that. Now this can be converted from degrees, minutes, and seconds into decimal form by computing each of these with their bases. So this example here, we're taking the whole number 18 and we're going to add to it 10 out of a total of 60 possible minutes. So 10 out of 60 minutes. And then we add 30. Now we've got 3,600 here because 30 or 60 times 60 is 3,600. And that's how we get that number. So convert like that and then add them all together, and there we have our decimal form of that. What we need to do, which I haven't done yet, is figure out, apparently on the TI-83 and TI-84, you can convert this using the angle, and you can convert from degree and minutes and seconds to decimal form. So we'll need to take a look and try that out. So let's give this a try with one other little example. Let's say I've got 6 degrees, 4 minutes, um, and sure, 30 seconds. There we go. So we would do 6 plus, and we would do 4 out of 60 plus 30 out of 3,600. Calculate all that, and that's going to give us our decimal form of this. Okay, I'll leave it at that. Bye.